Jumping into the vessel of space, there is an additional planet called Proxima B that has a climate basically the same as Earth and is situated in the livable zone of its star, Proxima Centauri. This star is outstanding for being the nearest star system to our own, after the Sun. This red dwarf star is located 4.23 light-years from our Sun, making it an interesting objective for cosmic investigations. The fact that Proxima B has conditions resembling those on Earth piques the interest of researchers and enthusiasts alike. Recent advancements in technology, especially the new James Webb Space Telescope, have empowered cosmologists to identify light radiating from the exoplanet Proxima B. This discovery could serve as proof that the planet is inhabited by extraterrestrials, igniting energy and interest in the potential for life beyond our planet. However, this finding is just one of the many exciting discoveries that the James Webb Space Telescope could offer us. As we investigate what our new telescope may uncover on Proxima B, it raises significant inquiries about the possibility of sending a manned mission to this distant exoplanet. Stay tuned as we delve deeper into this mysterious discovery by the James Webb. If you're enthusiastic about staying aware of the latest developments in the universe and its many wonders, consider subscribing to our channel. Remember to like this video and turn on the notification bell to stay informed. Now, what precisely is an exoplanet? An exoplanet is defined as a planet that orbits a star other than our Sun, which means it exists outside the bounds of our solar system. Among the exoplanets researchers have been exploring, none have drawn as much interest as Proxima B. The star associated with this exoplanet, Proxima Centauri, is classified as a red dwarf, characterized by its relatively cool temperature of 2,872 degrees Celsius. It is significantly less massive than our Sun and emits only about 0.001 times less light. The proximity of Proxima B to its star is crucial, as it exists in the habitable zone, where conditions might be right for life. For us, this zone is typically where liquid water can exist on a planet's surface, a vital ingredient for life. Proxima B has features that are remarkably Earth-like, including continents, seas, and possibly even life itself. The presence of auroras could give the planet a greenish hue in its atmosphere, resulting from intense flares emitted by its star. These stellar flares create a complex magnetic environment that could foster unique atmospheric phenomena. Curiously, Proxima B is tidally locked, meaning the same side of the planet constantly faces its star, much like how our moon orbits Earth. This results in a strange situation where conditions may be better for life. The surface temperature on Proxima B could range from -90 degrees Celsius to 30 degrees Celsius, creating a wide array of conditions. Completing one full orbit around Proxima Centauri takes roughly 11 Earth days, indicating a much shorter year than we experience on Earth. Furthermore, Proxima B has a gravity that is about 1.3 times greater than that of Earth, which would have implications for any potential life forms that might develop there. However, researchers remain uncertain about the exact nature of Proxima B's atmosphere. If it exists, it may contain essential ingredients like carbon dioxide, various minerals, and water crucial for the biochemical cycles necessary for life. Despite the excitement surrounding Proxima B, sending manned missions there remains a significant challenge due to the vast distance involved. Currently, a project known as Breakthrough Starshot is underway, backed by billionaire Yuri Milner. This initiative aims to create nanoprobes capable of traveling at 20% the speed of light. These probes would be designed to visit Proxima Centauri, offering a unique opportunity to study our neighboring star system up close. The proposed speed of these nanoprobes is around 16,000 kilometers per second, which would allow them to reach Proxima Centauri in just a few decades. Such a mission could provide valuable insights for future generations, unraveling mysteries about Proxima Centauri and its intriguing exoplanet, Proxima B. So, what could these nanoprobes reveal when they finally arrive? Interestingly, we have already begun receiving signals from Proxima Centauri. These signals were detected by the Parkes radio telescope during investigations into the star, which was emitting bizarrely strong flares that caught the attention of cosmologists, including Anderson from the University of California. He led the Breakthrough Listen project, which aims to search for technological civilizations in space, aiding our quest to understand if we are alone in the universe. This initiative is part of the broader search for extraterrestrial intelligence, SETI, involving the collection and storage of various signals from space to create a database for future research. The data collected has led to significant discoveries, especially when Shin Smith, a diligent student at UC Berkeley, began analyzing the signals during his work. He accidentally found an intriguing narrowband radio frequency emission at 982.551 MHz. Penn State University, who excelled in signal analysis, remarked that this specific signal represents one of the most exciting finds of the Breakthrough Listen project, as it deviates from the typical patterns we have observed before. The Parkes radio telescope operates by detecting signals over brief periods. During these observations, the telescope focuses on Proxima Centauri and then switches to observe different areas of the sky to confirm that any potential signals originate from the star itself. Sophia explained that during around 3 hours of observation, a signal consistently returned during 5 of the 30-minute intervals when the telescope was focused on Proxima. Conversely, when the telescope moved away, the signal disappeared, raising captivating questions about its source. This highlights the significance of the discovery. Space expert Dyer RIT from the University of Pennsylvania emphasized that observing this kind of signal, which doesn't come from Earth, strongly suggests the presence of advanced technology. Ongoing investigation of these signals aims to confirm their extraterrestrial origin, aided by the James Webb Space Telescope, which is being directed toward Proxima B. Researchers hope it may soon detect artificial light from the planet, providing further evidence of a potential civilization. Abraham L. from Harvard University underscored that if Proxima B emits artificial nighttime illumination reaching 5% of the natural daytime brightness, the James Webb could identify this light with an 85% certainty, which would be momentous. Proxima B is significantly smaller and dimmer than our Sun, affecting the configuration of its habitable zone. This unique characteristic means that the habitable zone is much closer to the star than it is in our solar system. Proxima B orbits at a distance of roughly 4.5 million kilometers from Proxima Centauri, leading to an orbital period of about 11.2 Earth days. Proxima Centauri is known for its active nature, producing fierce solar flares that could pose challenges to the potential habitability of Proxima B. Additionally, the exoplanet's close proximity to its star results in extreme temperature variations, with the daytime side being scorching hot and the nighttime side freezing cold. These drastic temperature changes could have significant implications for the planet's ability to support life. Proxima B stands out as the exoplanet that captivates the attention of cosmologists and scientists due to the wealth of data gathered about it. However, it is not the only exoplanet that shows Earth-like conditions that may support life. Within the Milky Way galaxy alone, a total of 55 potentially habitable exoplanets have been confirmed, with many more yet to be discovered. As our technology advances, we continue to search for and identify these distant worlds. For example, in our neighboring Andromeda galaxy, which has features similar to our own, there remains significant potential for habitable or inhabited planets. Moreover, within the larger structure of the universe, superclusters of galaxies present even more possibilities. The Milky Way belongs to the Local Group, a cluster of around 40 galaxies, which is itself part of the local supercluster, containing approximately 100,000 galaxies. Remarkably, estimates suggest that there are around 10 million superclusters throughout the universe. This prompts significant investigation. If the Milky Way is relatively modest in size and currently has 55 confirmed potentially habitable planets, just imagine the countless habitable planets, or even those hosting life, across the vast expanse of the observable universe. The significance of finding exoplanets lies in its potential to expand our understanding of our place in the universe and to answer fundamental questions about life and existence on other planets. The ongoing investigation of exoplanets allows us to explore the vast diversity of planetary systems and examine the possibility of new forms of life beyond Earth. Additionally, these discoveries can enhance our understanding of how planetary systems form and evolve over time. The implications for the search for extraterrestrial life are profound. Exoplanets serve as critical candidates for harboring life and can provide essential information about the conditions necessary for life to thrive elsewhere. Ultimately, the exploration of exoplanets empowers us to test our existing hypotheses and models regarding the formation and evolution of planets and celestial systems, fundamentally advancing our comprehension of the universe and our role within it. Investigating the vast realm of our universe has always sparked human curiosity, pushing us to seek answers about our reality and the potential for life beyond Earth. The mission to discover new worlds is not just a scientific endeavor, but a philosophical one that challenges our understanding of life, habitability, and the universe itself. As we venture further into the realms of space exploration, our advancements and methods continue to evolve, enabling us to gain insights that were once unimaginable. Recent missions to various celestial bodies within our solar system have provided valuable data about planetary conditions. For instance, the Mars rovers have unveiled evidence of ancient rivers and lakes, suggesting that the red planet may have once harbored conditions suitable for life. Furthermore, missions to the outer planets, like the Juno spacecraft orbiting Jupiter and the Cassini probe studying Saturn, have revealed intricate details about their atmospheres, magnetospheres, and moons, some of which may also hold the potential for life. The diversity of these conditions highlights the myriad ways in which life could potentially emerge. The quest for exoplanets has also transformed our understanding of where life may exist. Kepler's mission alone has discovered thousands of exoplanets, many of which reside in their stars' habitable zones. These discoveries have broadened the definition of what constitutes a potentially habitable world, allowing researchers to consider various factors, such as the presence of moons, atmospheric composition, and geological activity. One captivating aspect of the study of exoplanets is the concept of biosignatures, indicators that suggest the presence of life. Scientists are developing methods to analyze the atmospheres of distant worlds, searching for gases like oxygen, methane, and carbon dioxide that could indicate biological processes. The potential for using telescopes like the upcoming Extremely Large Telescope, ELT, or the Roman Space Telescope to search for biosignatures is generating excitement in the scientific community. These observations could revolutionize our understanding of life's distribution in the universe. In addition to direct observations, the field of astrobiology has gained momentum, examining the conditions that could allow life to thrive elsewhere. Researchers are studying extremophiles, organisms that can survive in extreme conditions on Earth, such as hydrothermal vents and acidic lakes, to better understand the limits of life. This research informs our search for life in previously considered inhospitable places, such as the icy moons of Jupiter and Saturn. Enceladus and Europa, in particular, are of great interest due to their subsurface oceans, which could harbor microbial life. As we look to the future, colonizing other planets becomes increasingly plausible. Projects aimed at sending humans to Mars, such as SpaceX's Starship and NASA's Artemis program, envision a sustainable human presence on the Moon and beyond. These initiatives not only aim to push the boundaries of human exploration, but also to establish a permanent human foothold in space, preparing for further exploration of the solar system and beyond. Moreover, the potential for finding life beyond our planet raises significant ethical and philosophical questions. What would it mean for humanity to encounter extraterrestrial life? How might we approach communication and cooperation with intelligent beings? These questions are not merely speculative. They are vital considerations for future missions. Establishing frameworks for ethical engagement with extraterrestrial intelligence is a topic of growing interest among scientists and ethicists alike. Furthermore, the ongoing discoveries in the field of exoplanet research challenge our understanding of planetary systems. The presence of unusual planetary configurations, such as hot Jupiters, gas giants that orbit very close to their stars, complicates existing models of planet formation. These anomalies prompt researchers to reevaluate the dynamics of planetary migration and the impact of stellar interactions on planetary development. The concept of the Goldilocks zone, where conditions are just right for life, is also being reconsidered. Research suggests that life could exist in a broader range of conditions than previously thought. For example, subsurface oceans on icy bodies could provide stable environments for life, and high-energy conditions such as those found around black smokers on ocean floors could also support diverse ecosystems. Public interest in space exploration has grown significantly, fueled by captivating images from telescopes and inspiring stories of missions like the Perseverance rover and the James Webb Space Telescope. Social media platforms enable scientists to share their findings and engage with the public, fostering a global community passionate about cosmology and exploration. As our understanding of the cosmos continues to expand, the implications of these discoveries are profound. The potential to uncover new exoplanets that could harbor life not only challenges our current scientific models, but also encourages a reevaluation of our place in the universe. While Proxima B is one of the most exciting examples, it represents just the tip of the iceberg in the broader search for habitable worlds. Advancements in space telescopes, such as the James Webb Space Telescope, have opened up a wealth of data that allows astronomers to study planets in unprecedented detail. This shift in observational power is transforming the search for life, enabling scientists to focus on planets that were previously unreachable by conventional methods. In addition to identifying potentially habitable exoplanets, a growing area of research is focused on understanding the diverse environments where life might thrive. For example, the concept of life as we don't know it is becoming increasingly plausible. Scientists are no longer limiting the search for life to planets that mimic Earth's conditions. Instead, they are expanding the criteria to include environments with extreme temperatures, pressures, and radiation. This shift is largely inspired by the discovery of extremophiles on Earth, organisms that live in environments previously thought to be inhospitable, such as volcanic vents, acidic lakes, or the frozen tundra. These findings suggest that life may not require Earth-like conditions, broadening the scope of the search to more exotic worlds. One particularly intriguing area of research is the study of exomoons. These are moons orbiting exoplanets that themselves may lie in the habitable zone of their star. Many exoplanets, particularly gas giants, have large moons, and these moons could possess the right conditions for life. Exomoons, therefore, represent a new frontier in astrobiology. The idea of a thriving ecosystem on a moon, perhaps even more stable than the host planet itself, is a concept that is beginning to gain traction. As exploration of exoplanets intensifies, the next big challenge lies in developing the technology to send spacecraft to these distant worlds. While current missions like Breakthrough Starshot are making progress, reaching planets in other star systems requires significant advances in propulsion systems and spacecraft design. Research into nuclear fusion or even laser-powered sails could one day make interstellar travel a reality, opening up entirely new possibilities for humanity. Such advancements may not only provide us with the tools to study exoplanets up close, but also potentially bring us closer to finding life elsewhere in the universe.